Welcome to the afternoon session on quantum information and computation, or whatever the hell it's called. Our first speaker is Tanner Crowder, and I want to properly introduce him the way that I introduce people. So, he came to NRL right after finishing his undergraduate degree in math, right? No background in quantum mechanics, no background in information theory, no background in groups, other than like a group is, right? And so I thought it would be really funny, right, since they assigned him to work with me, to ask him to characterize the groups whose convex closures can be embedded in a set of qubit channels, right? So after we actually understood what the problem meant, he came to me and said, "Key, is this actually solvable? Can you do this?" I said, "Well, I don't know, like, do it, right?" Anyway, the thing is, like, so he's not big on, like, words or writing things out exactly, or like, right? He reminds me of this guy a lot, Bob, right? Like just chicken scratching. But he actually really impressed me, right? He solved this problem, hard problem. And then I told him, I said, "Okay, well, we're going to go to this conference, and I'm going to give the talk." And he was happy to hear that, because he didn't want to give the talk, right? Actually, until last night, late. And then I kind of like, maybe he'll tell you more about that. But he sort of found out late last night, oh, actually, you're giving the talk, Tanner. So, please. Right.
Thank you for that good introduction, Key. What?
What do you think the whip's for? It's symbolism.
Yeah, Key's right. Last night, he duped me into giving this talk. We got, really good and drunk, and he was like, "Tanner, you're giving the talk," and we kind of laughed about it. And this morning, I woke up and the slides were in my inbox, and it said, "Good luck, I'll see you at 2." And like, originally I felt bad because Key was giving the talk, and he had prepared all the slides and everything. So I was like, "Key, can I do anything for you?" This was before, I even got to Oxford. He was like, "No, I got to cover making slides, giving the talk." So this is kind of a little bit of a surprise to me, much like finding out Key's real sexuality. These slides were actually prepared by Key, so I'll take any compliments, he can take any criticisms, and here it goes. So let me be pretty clear about the question that I was asked 7 months ago. The question is which groups of classical channels can their convex closures be embedded into the quantum, the qubit channel? And we solved this in a series of steps. The first was we solved it for the cyclic groups, then we moved to the abelian groups, and then we just solved it for, groups in general. A little motivation behind why we even care is, we have a set of all qubit channels that are certain affine transformations of the unit ball via the block representation. One of these subsets is called the unitable channels, and that are those F where B equals 0 in the 3x3 real matrices. And so examples of unitable channels are projected measurements, bit flipping, phase flipping. And really the reason why we care about unitable channels is because we can calculate the scope of a unitable channel pretty easily. And real quickly, I'll diverge and kind of explain what scope is every basis in the state space can be used to transmit classical information, and for every basis, it emits a classical channel. Every classical channel has a unique capacity associated with it, and the set of all capacities as we range over the basis in the state space gives it a scope. Now, calculating the scope of a unitable channel is reduced to actually just calculate the scope of a symmetric unitable channel. And an interesting property about the symmetric unitable channels is that every symmetric unitable channel lies in the convex closure of a copy of the Klein-4 group. Moreover, for the convex closure of every copy of the Klein-4 group is isomorphic to an affine monoid of the classical 4-4 channels. And this actually gives us a classical representation of a qubit channel, and we can actually calculate the scope pretty easily from this by just calculating the eigenvalues of its associated classical channel under this isomorphism. So, the question now arises, well, we have this nice convex linear isomorphism from the Klein forward group of classical channels into the quantum channels. Well, what other group has this property? So we're going to say for a group G of classical channels, there's a function from the convex closure G into the quantum channels such that it preserves the identity matrix, products, convex sums, and is injected. And for this such function, we're going to call it an embedding. Now, just so there's no confusion, when I actually later on refer to embedding a group, I mean taking this function and embedding its convex closure into the quantum channels. Now, this isn't just a trivial problem because the quantum channels contain groups of arbitrary large order. An example of this is the dihedral group of order n. So there are quite a few of them. And we went about answering this question by just proving, little baby steps, and this was the first one. And if G is a group where there's an embedding, G must be finite because it's a collection of permutation matrices, and the image of the convex closure of G is contained in the convex closure of SO3. So in particular, the image of phi, all the channels are unital. And as we can see, SO3 contains an infinite number of finite subgroups. We can just take a rotation about, a infinitesimal angle, and there's your group. So for instance, the cyclic groups are in there. And so we asked, well, what cyclic groups can we actually embed? And it turns out that there's only two of them, and it's Z2 and Z3. And the reason why is because there's a generator for Zn when n is greater than or equal to 4. This equation holds quantum mechanically, but will never hold classically. It actually implies that one of the matrices would have to be negative, and you can't have that for a permutation matrix. So that's really the reason why. And because we have the classification of finite abelian groups, we can actually cancel out a lot more abelian groups, and we're left with only abelian groups whose convex closures can be embedded are now Z2, Z3, and the Klein 4 group. So there's only one more. And due to the classification of finite abelian groups, we can see that if a group G has order divisible by prime P, and the prime is greater than or equal to 5, it has a cyclic group of order greater than or equal to 5 as a subgroup. So therefore, we can't have it. A little more analysis of this is we can see now that there's only two cases we have to consider. And that's when we have powers of Z2 and powers of Z3. And when I say powers, I mean the direct product. And it turns out that when you have Z2 cross Z2 is the only power of Z2, except actually Z2 itself, that is able to be embedded. And it's because it would imply that there is more than 4 commuting involutions in SO3, which is not the case. There's only 4 of them because they have to be simultaneously diagonalizable to commute. And this next part, where we're looking at the powers of Z3, was a pretty big barrier. I think he and I worked on it for maybe 2 weeks or so. And then so I was in Key's office, and he asked me in front of some people that, I kind of wanted to impress, if you know what I mean. And he said, Tanner, you can't prove this. Kind of challenging my masculinity. And I was like, Key, screw you, I can't. And so I went back to my office, and 30 minutes later, I was able to prove it. And so my masculinity was therefore reinforced.
Was she impressed?
I don't know what you're talking about.
You're on camera, Tanner.
Yeah. So it turns out that the direct product of Z3, any more than once, so just Z3 itself, is the only group that we can embed because it would imply that there's 2 commuting generators of Z3, because Z3 cross Z3 has 2 distinct subgroups of Z3. But it turns out 2 commuting generators actually just generate the same subgroup of Z3. So that's pretty much why we can only have Z2, Z3, and the Klein 4 group. So next, we wanted to move on to the non-abelian groups. And due to the Silo theorems, we can actually rule out any non-abelian group that doesn't have order 12 or order 6. Unfortunately, it's not as nice as the finite abelian, the classification of finite abelian groups, because it doesn't actually tell us what groups we can embed. This just tells us that it's restricted to order 12 and order 6. Now, there's only 2 groups of order 6, and that's a cyclic group on 6 elements, and the permutation on 3 elements. And then order 12, there's 5 groups of order 12, 2 of which are abelian, which we ruled out already, 3 of which are non-abelian. And of those 3, 2 of them have cyclic subgroups of order greater than or equal to 4. So we can rule out all groups that are non-abelian except A4 and S3. Now this doesn't mean that A4 and S3 are embeddable. To prove this, it actually took a lot more work, and we had to actually come up with explicit matrices in SO3 that generated A4 and S3, and also in the classical case. So this wasn't just about saying that, you know, A4 and S3 were in SO3, because that's not a novel fact. I think that was proven by Hoxter in sometime in the 50s or 60s. I'm not exactly sure when, but so it's not a novel fact, but we actually had to find them, specific groups, and see if there was a convex and linear isomorphism. So we took the natural set of even permutations on 4 elements to create A4. And then to construct the copy of A4 and SO3, we took the block representations of the involutions and the basic circulant matrix, which generated a copy of A4 and SO3. And we're just going to use the natural isomorphism where, you know, the identity goes to identity, X goes to spin X, and so on. So now we have to show whether or not we have a convex linear extension of this. And we ended up, after some grueling calculations to find these matrices, we ended up finding that any matrix that is in convex closure A4 has to have this form where the probabilities E, C, C2 have the same, that are assigned to each matrix, have the same name as their matrix, except for where it just kind of create clear inconsistencies. So like C is the probability of getting the C matrix. And so it turns out that its image in the convex closure of G has this form. Now, the fact that that's even a function, let alone an isomorphism, it's pretty astounding to me, I think. I mean, I don't know any way to see it off the top of my head, but you know, after some black magic that he and I did, we were able to prove that it was a function and an isomorphism. So it turns out that the convex closure of A4 can also be embedded in Q. Now, if we recall, A4 has 3 subgroups, non-trivial subgroups. It has Z2, Z3, and the Klein 4 group. And these are the abelian groups that we said could be embedded. So this actually kind of reinforces what we said before. And, you know, due to this and the next slide I'm going to show you, it kind of makes us think that A4 is the only group that we can embed, you know, and its subgroups. So we took the natural copy of S3, which is just permutations on 3 elements, and we showed that this convex closure cannot be embedded into Q because we found an equation that holds for the classical channels, but will never hold quantum mechanically. Now, if you remember when we were doing the cyclic groups, we found an equation that held quantum mechanically, but never classically. So this kind of reverses our intuition about this isomorphism. So it turns out, though, that you can never have a convex linear isomorphism between S3 and the classical 3-3 channels and the qubit channels. So we then went up a dimension. and we said that any group G that's a copy of S3 in 4 dimensions is actually conjugate to what we call the natural copy of S3 in 4 dimensions, which is where we just hold the first element fixed and we commute the other 3. And since it's conjugate, we have this equation that holds as well in the classical channels, but not quantum mechanically. And so at this point, I'm pretty convinced that there's actually no embedding for any dimension of S3. And so I tell Key, and Key's like, okay, I kind of believe you. And so we write up our abstract and submit it to this conference, and we actually said that S3 was not embeddable into SO3. And yeah, but we were able, I tried to show it a lot with some loose math and cycle decomposition, but there was actually no avail. I really thought that all groups of S3 were conjugate to this natural copy where it just holds all elements but 3 fixed. And yeah, and so he said, well, that's not good enough, we need an actual proof. And so I said to him, Key, we're going to have to, go up dimension, and you're going to have to do some calculations in 5 matrices. And he told me no, that that's not how it was going to go, and that I was going to have to do some calculations in 5 matrices. And so when I say we prove this next theorem, I use we very, very loosely. And so we constructed this unorthodox copy of S3 in 5 classical channels, and we'll denote the order 3 elements with the identity and hold the first 2 elements fixed and then commuting the other 3. And the involutions are going to be the natural involution, or the 3-3 involutions in the flip matrix. And then we're going to construct a copy of S3 and SO3 by just negating the original involutions in S3. And that's because the previous involutions had determinant -1, and it turns out they have to have determinant +1 to be in SO3. So we did that, and we signed probabilities to them like this, and it turns out that if this is in the convex closure of G, then its pre-image has this form. This is an isomorphism, once again, and right now it's actually not at all clear to me physically why we could, we could independently fix the sums x0, x1, and x2, and x3, x4, and x5, and it gave us it's going to give us some information physically that we didn't have before. I mean, mathematically I understand why, because it actually, just doing calculations, it's pretty clear why it's an isomorphism, but physically I don't know what that changed. I really didn't expect it to be that way. And so it turns out that the convex closure of S3 can also be embedded in the quantum channels. So this leaves us with the answer to our question. There, essentially are 2 groups that can be 2 groups of classical channels that can be embedded into Q, and that's S3, A4, and their respective subgroups. So I think that's it.
Are there any questions? Yeah, Peter. Yeah.
So, can you go back to A4 or S3?
Yeah, sure.
So there's a theory of group representations, and it's exactly about how you can represent groups as groups of matrices.
Yeah.
And there's actually a lot known about this. So, for example, it's known. So every group representation can be written as a direct sum of irreducible group representations, and there are all kinds of classical theorems about how many there are of each kind. For example, S3 has 2 irreducible ones of dimension 1 and 2 irreducible ones of, or 2 copies of the irreducible one of dimension 2. So that phi of f that you have there is actually a direct sum of a 1-dimensional and a 2-dimensional representation, and that other f is also a direct sum. For example, you can see that in the 5 by 5 matrix in the bottom.
Yeah.
Everything has a common eigenvector 1, 1, 1, 1, 1. Right? for every value of x0 to x5, 1, 1, 1,
Yeah.
1, 1 is always an eigenvector. So if you just change the basis and you factor out this eigenvector, that matrix F can be written as a block of a 1 by 1 and a 4 by 4. And if you further subdivide the block 4 by 4, you get 2 2 by 2s. Okay. So probably group representation is something you should look at. Now, it's usually done in the complex numbers. So here you're doing it with real coefficients, so there's still something. It's not always clear that the general method always works for this. But there is a general method, and there are lots of theorems about that.
Are there any questions? Okay, let's thank the speaker again.